Hey guys, what's going on? So in this video, I'm going to talk about whether FPGAs can compete with GPUs in image processing. And rather than doing any analysis of my own in this video, I'm just going to look back at the literature on FPGA and GPU comparisons, specifically at case studies on sliding window applications, and see what previous papers have to say, and then in some later videos we'll do analysis of our own. So just to start, the class of applications we're looking at in image processing are called sliding window applications. So basically, these are applications like the one shown on the left, where you have a sequence of for loops that's iterating over an input, in this case called in, and writing values to a multidimensional array called the output in this case. And each pixel, or each entry in the output, is a function of some fixed size window of input, and we're basically stepping over the windows of the input, in this case 2 by 2 squares, and producing windows of the output. So in this case, we're blurring together 2 by 2 squares of the input to produce an output. So how do FPGAs and GPUs do comparatively on these kinds of applications? So there have been a few different papers that I found that do basically almost micro-benchmark case studies where individual sliding window applications are tried on FPGAs and GPUs, and the authors report the results. So here's one that came up as pretty highly cited. It's a trade-off analysis of FPGAs, GPUs, and multi-cores for sliding window applications. And it was published in the ACM Transactions on Reconfigurable Technology and Systems in February of 2015. And the punchline is the results show that for large input sizes, FPGAs can achieve speedups of 5.6x and 58x compared to GPUs and multi-core CPUs respectively, while also using up to an order of magnitude less energy. For small input sizes and applications with frequency domain algorithms, GPUs generally provide the best performance and energy. So here's one of the charts for 2D convolution implementations on GPUs, FPGAs, and CPUs. And they use 3 different image sizes, 480p, 720p, and 1080p. And each of these charts has the same structure. It's the size of the window. So the numbers down here, like 2, 16, and 30, are the dimensions of the window. So 2 would be a 2 by 2 window like here, and 100 would be a 100 by 100 window. And then here's the log scale of frames per second. And they did 6 platforms, an FPGA, a GPU, a 4-core CPU, a single-core CPU, a GPU operating and doing convolution in the frequency domain, and a 4-core CPU doing convolution in the frequency domain. And overall, the FPGA is pretty much in the middle of the pack, with the GPU in the frequency domain having the best performance as window sizes get large. And then here's the same plot, but instead of 3 different image sizes, these are 3 different applications, and instead of measuring frames per second log scale, this is a linear scale power consumption, and the FPGA is very low on power consumption. It's down there with the single core CPU, and the power consumption really doesn't change much across applications and doesn't really change at all. Well, I guess it just slightly changes for core entropy here, but maybe that's even just a plotting anomaly. But basically very stable power consumption at about 150 watts and quite low compared to the GPUs. Here's overall system energy consumed processing 1 frame for each of the 3 applications. So again, same platforms and same chart structure, but now we've got log scale energy consumption in joules. And so for 2D convolution, FPGA is just kind of in the middle of the pack. Actually, it's sort of more jumpy, but basically tracks the performance of the GPU in energy consumed per frame. And this is all 720p images. And so for some of absolute differences in core entropy, by the time you get to very large window sizes, the FPGA is consuming a lot less energy than any of the other platforms. However, I'm not sure how realistic some of these are, considering that, the FPGA on some of absolute differences doesn't start winning until you get out into the, the high teens in window sizes compared to a GPU. And similarly for core entropy. And having looked at a lot of image processing applications, I'm not sure how common window sizes, fixed window sizes that large are. Here's another one, which is a similar structure, except instead of testing on multiple different sliding window applications, they just did one, which was a Gaussian filter or Gaussian blur. And this is all fixed point arithmetic, which probably favors the FPGA since GPUs have built-in support for floating point that's much better than FPGA's support for floating point. And here's a bunch of different image resolutions. Basically, the punchline of this chart is that the Gaussian filter processing time is the best for the OpenCV CUDA implementation, which is the GPU, but it's best for the FPGA if you take into account the time required to load the image. Now, for a larger, more compute-intensive pipeline, you could double buffer the images so that you could cover some of that latency. So this might not hold up for larger, more compute-intense pipelines. But again, another interesting data point about the relative cost of loading data and the relative performance of FPGAs and GPUs on sliding window apps. Here's another very similar study, which was the last of the sort of sliding window micro benchmarks that I wanted to cover, which was implementation of 2D convolution on FPGA, GPU, and CPU by Ben Cope at Imperial College London. And here are the two critical performance charts, and they're actually very similar to the first paper. So basically, they're organized by window size, and here are a bunch of GPUs, and then here's a Pentium 4 CPU, and then here's two FPGAs. And what you see is at very small window sizes, like 2 by 2, the large GPUs are doing way better than the FPGAs. But by the time you get out to 11 by 11 window sizes, you start seeing GPU performance deteriorate a lot more than FPGA performance. So, the larger GPUs are down in the neighborhood of a few megapixels per second, while the FPGAs are in the neighborhood of a few dozen pixels per second. So my takeaway from all of this was basically large window sizes or large fixed window sizes favor FPGAs because they're kind of a mismatch for the GPU microarchitecture. It puts a lot of stress potentially on, the register file if you have tons of large windows floating around. And also, if you have very large windows, you can potentially have large ranges of dependencies, which means that it's hard to do things like cut the image up into vertical strips that are independent and process each one independently, right? It basically means you have more duplication at the edges of the strips, which makes a GPU schedule tougher. So does this actually translate into higher performance on real applications? Because as I was saying about the first paper, the sort of benchmark comparison for SAD, core entropy, and convolution, what fraction of the operations in a big image processing pipeline are convolutions with window sizes that are more than, a dozen by a dozen, or sliding window operations with window sizes that are larger than maybe a dozen by a dozen? And I'm not so sure that that's common enough to outweigh the other performance benefits of a GPU, but we're going to look at that next time when we look at some other papers that are on case studies at implementing larger whole applications on FPGAs and GPUs. So I'll see you in the next video.